All right, our next talk is by Gaspard Duchene, and he'll be talking about HST imaging of new edge-on circumstellar disks in nearby star-forming regions.
And in fact, you got it right, Meredith. I'm not Gaspard, I'm Paul. I'm Karl Stapelfeldt for the next 15 minutes. He was the one supposed to be here, as you can see in the schedule. Obviously, he's been sequestered, so that means he's locked in his office, not allowed to come across the border. He's not even allowed to go to Hawaii or Alaska. So here I am, standing in front of you. I'm trying to do a good job at representing him. But I want to point out as well that Marshall Pren and Skylar Wolf are also in this room and are part of the same project. So if you have questions, you can also direct them to them. So I'm going to present you the talk that Karl has prepared. So very little changes from there. And what I want to do is report on, good. Another one? All right. I want to report on the results of an HST proposal, a program that we've conducted to get new images of edge-on protoplanetary disks. And obviously, there are images that are spectacular, like the HH30, the very well-known one. But what I want to do is find new ones and show you that we've actually almost doubled the number of edge-on disks that have been imaged with HST. Well, except that this one doesn't work. So it was working, yeah. All right. It's all right. So the big advantage of edge-on disks is that they act as nature's occulter. They block the starlight for you, so you don't get to have a contrast problem, and you can actually image a disk right away without having to resort to very complicated observing sequences. So that's beautiful. That's very practical. Besides being practical, you can learn a lot from the images of edge-on disks. And in particular, you can get right away information about the vertical structure of the disk, because that's what you're looking at. You're looking at the disk from the edge. So you can see the vertical structure, the flaring, some amount of settling. If you combine scattered light images with other type of data, including SED modeling, and most importantly, redshift transfer modeling, then you can infer a lot about the properties of the disks. Surface density profile, the dust properties, certainly in the surface, by extension potentially in the midplane or closer to the midplane. And so you can learn a lot about those disks. So that's one of the reasons why we've been using edge-on disks to understand the nature and the structure of this protoplanetary disk for the last 20 years now. Now, one other thing that is worth noting is that only about a dozen or so disks have been imaged in scattered light as edge-on disks. Most of the other data you can see are from disks of other inclination that do not necessarily allow the same type of observations. But if you run simple statistics and you assume your disks are randomly oriented in the sky, you should get many more edge-on disks than that. So clearly we're missing something, because we know thousands of stars with disks, and we only know a dozen or so edge-on disks. So we're missing them somehow. And this project is trying to provide some new information towards filling that gap. So you're probably all familiar with the beautiful picture of HH30 obtained about 20 years ago now. It was actually a serendipitous discovery, because they were not actually imaging HH30, but it still started a big field. It validated the basic understanding we have of disk of being flared structure towards the outer edge. They're driving jets perpendicular to the disks. And by doing modeling, redshift transfer modeling, to try to interpret the observations you can see in the image here, you can infer the dust properties, the grain size at the surface of the disk. And that has spawned a number of papers just on HH30. But of course, like I just mentioned, there's more than one disk that is edge-on that's been imaged. There's a dozen or so. And we've learned a lot of things through these various disks. We've learned that disks in multiple systems tend to be small, compact, probably due to tidal truncation. We've learned something about the grain size distribution that tends to be focused or biased towards smaller grain size in the least evolved objects, and we've learned that basically the vertical structure is indeed pressure supported, as you would naively assume, although there are a couple of exceptions where things don't seem to line up too well. Like I said, we've imaged a dozen or so of these disks. That's nice. We've got beautiful images, and we can make nice pictures of them. But it's not quite enough to draw statistics. If you're interested in trends versus, say, mass of the star or evolutionary stage or something like that, you need more than just a dozen sources, or otherwise you're going to end up with bins with one object in each, and you're not going to be learning too much about it. And so you need to get more of those. And as just mentioned, there should be many more of those out there. We just haven't found them. And the reason is, and the question is now, how do we go about finding new ones? And this is where Spitzer came into the equation. So about a decade or so ago now, Spitzer has pretty much mapped every single big star-forming region in the vicinity of the sun. We've observed thousands of stars, and when I say we, I mean collectively the community, not myself, in all of these clouds through these big projects. And as part of the thousands of stars that have been identified as young stars with a disk, we've recovered all of the edge-on disks that were known before Spitzer. And so we can take that into our advantage and look at what the spectral energy distribution of this edge on disk look like from the near infrared all the way to the far infrared. And as it turns out, here are 3 examples. Probably the most famous one, HH30 is at the top, and they all show exactly the same structure, which is going from the optical here to 100 micron here, 1 bump, a trough, and a second peak out there. And it's a very same structure in all 3 of these plots, and if you put more edge on this, they look again the same. And what you're seeing is scattered light with little to no extinction from the optical all the way to 10 micron, and then outside of 10 micron, then you see far infrared thermal emission that pierces through the disk. Okay? So the fact that these known edge on disk share the very same or very similar spectral energy distribution gives you a tool to select new objects. You can go about and try to find objects with spectral energy distribution matches those, and then say, well, they're a good candidate to be edge on disks, so let's go and image them. And so that's exactly the goal of this project. What Karl has done, and I emphasize that this is really is part of the work here, is looked at 2,000 or so spectral energy distribution of Spitzer-identified young stars with a disk. And is looked at, I don't know how many plots like those, looking at one by one and figuring out that some of these do have 2 bumps, kind of like the ones we see in the known edge on disks. And so he's identified those as candidate edge on disks that are worthy of follow-up imaging to see if they're really edge on disk systems. So the sample that is devised gave us a median SED again with 2 peaks, one in the near infrared, one in the far infrared, that is similar to HH30 or IRSO4302, which is another famous edge on disks. And the point to emphasize here is that at far infrared wavelength, these edge on disks are exactly the same flux as the regular T-Tauri star disk, which are shown at the top curve here. But of course, in the near infrared, because we see only scattered light, we see a much reduced flux. So that's why Spitzer was so powerful at finding at least the candidates, is because it was sensitive at these wavelengths out there, where edge on disks just look like normal disks. So it's easy to pick them up. So based on that, after identifying something like 70 or so pretty good candidates out of the Spitzer database, we selected 21 that we thought were the best candidates to follow up with HST. And we went about and gotten data with ACS, 1 orbit per star split between 0.6 micron and 0.8 micron. That gives us information on the disk, and on the jet. So we can see the 2 features, the main features of an edge on disks. And to make a long story short, the success rate is actually very high. Out of 21 targets, we've identified 11 of them as a result edge on disks, 9 of which are new. So we've almost doubled up the number of edge on disks imaged with HST in scattered light in this process. Of course, there are a few contaminants out there, including one where the infrared excess is coming from a background galaxy, so that was to be expected. It couldn't be 100%, but I would say that 50% success rate is pretty good in the first place. So if we got that many disks, of course, we're getting a good sense of the diversity of the sources, and I guess the contrast that won't show up too well in this plot, but you get a wide range of things. You get things that look a lot like HH30, just a little bit smaller in the plane of the sky with a nice nebulosity and a jet that doesn't show up too well here, to things that are very diffuse but with a very clear dark lane bisecting the region here, more like IRSO4302. So you get all sorts of objects, each of them is interesting in itself. And we're in the process now of following some of them and getting more observations and doing modeling, and that's what I'll spend most of the rest of the talk talking about. So the first couple of objects I want to talk about are both located in the Chameleon star-forming region. They're very clear edge on disks. You can see a dark lane going here and another one going here. But these 2 stars differ a lot by their appearance. One of them has very flat 2 nebula, top and bottom surface of the disk, whereas the other one has a lot of curvature to it. On the other hand, this one has a very prominent outflow going out here, whereas the other sources has a little bit of an outflow, but it doesn't show up too much. It's quite a lot fainter than the other source. So again, this emphasizes the diversity of what this edge on disk look like. Now the object on the right was picked up as particularly interesting for follow-up because it has a very nice, smooth and symmetric structure, which is something that doesn't show up in all edge on disks. A lot of these disks are very asymmetric, left to right. That's probably because they're just intrinsically not axisymmetric in the first place. But modeling something like that is very complicated. It gets very ad hoc. You need to guess why it's asymmetric. So when we see this that's actually very symmetric, we're very happy because that makes our life easier. We can use axisymmetric disks. So we followed up on that particular object and started some pretty extensive modeling. And without telling you too much about it, I encourage you to go and check out poster 139 by Skylar, where she's presenting a lot of the modeling she's done on that particular object. The one point I want to emphasize about this modeling was the interesting finding or conclusion that to match the images we see in HST, we started first by using a structure, the structure of the disk, there's a very sharp outer edge. So far, it had worked in previous edge on disk. We're very happy with it, so we started with that. It didn't work. We just couldn't get a good image out of that would match the data at all. This is illustrated in the sharp edge model over here, and doesn't extend quite far enough on the sides here. And this has led us to introduce a structure that's more reminiscent of what people have suggested in the millimeter we've heard about earlier from Sean, with a tapered edge model with some form of exponential decay that produces some amount of scattered light further out away from the center of the nebulae that matches much better with the observations. So that's one object, and again, go check the poster for more detail. A couple of other interesting objects are disks, edge-on disks, found in binary systems. I mentioned earlier in this talk that disks and binaries are frequently found to be compact. This is the case in that particular system where the separation of the binary is about 200 AU, but there's a very compact edge-on disk right here, about 60 AU across. So that's pretty small, but it still drives a very prominent outflow. Again, the contrast in the video here doesn't show up too well, but it's very sharp on the image I have on the screen. So very spectacular jet, very compact disk in a binary. Talking about binaries, arguably the most impressive object is probably this HH48 region over here, where there is a 320 AU binary separation, two beautiful jets, very misaligned from one another. So that's certainly telling us something about formation mechanisms of multiple systems, and by consequence, telling us something about planets in binary systems. But maybe the most important or interesting feature of that object has to do with the edge-on-disk object itself. Over here, where you see a nice dark lane, you can see the scattered light is very asymmetric left to right. That could be due to interaction with the companion. Wouldn't be entirely surprising. But most interestingly, if you focus on where the midplane of the disk is located, right here, and the jet direction, you'll notice that they're actually not perpendicular to one another. And there's an offset in the angle by something like 6 degrees. The exact explanation of that is not clear to me. I'm sure theorists will have plenty of words to say about that. I'm sure it has to do with the presence of a companion next to it, although maybe other ideas could be thrown out. Another intriguing object we've been working on is located in Ophiuchus, and it is another very clear edge on disk. You look at the image, you're like, bingo, this is your two top and bottom nebula of the disk, and nice dark line in the middle. That's pretty clear. One interesting thing is that this object popped up out of the Spitzer SCD database the same way we selected all of our targets. So very nice, very well populated SCD. But there's almost no other information on that source in SIMBAD. Nobody knew about that object. It was somewhere in the Spitzer database, and that's about it. So we tried to get as much as we could out of it, but it was not so easy. There's no jet. We cannot see any jet coming out, all right. We have a hard time finding any millimeter flux. We actually are resorting to getting camera observation right now to try to fill that part of the SCD. And the modeling that has been started by John Christ, and illustrated here in this on-off, showing the data in the model movie, showing that we can reproduce pretty well the morphology of that edge on disk, but we have to resort to a pretty small scale height, to the point where we think there is probably vertical settling. Now, the most intriguing part about this object is that we've just gotten 2 weeks ago an optical spectrum of that source, because we didn't know anything about it. It turns out it doesn't even have H-alpha in emission. So it looks like a weak-line Titari star, and yet it has a booming, clear edge-on disk right there. So what does it mean? I don't know. It looks like a non-accreting disk to me, but maybe there's other ideas out there. I'll spend I'll flash for 30 seconds all the beautiful images I have in my poster, so you can just come and talk to me at the poster session this evening with a glass of wine or something else. We've got a lot of data on this object. It's very intriguing. It's beautiful. It's large. It makes a nice picture. But all sorts of things we don't quite understand about it, and we're working on the modeling as we speak. So come and see me. I'll be happy to talk some more about it. Just to wrap up, I want to emphasize that we're going to be publishing a paper showing all the HST images, just the empirical results soon. At the same time, we're getting more follow-up observation in the near infrared, in the millimeter, and we're continuing the modeling effort to try to constrain the disk properties. And I'll leave you with that last slide of conclusions, insisting on the fact that we've been highly successful at using the SCD to finding this edge on disk. 50%, in my opinion, disk imaging with HST is quite a high success rate. And most importantly, by doubling the number of edge on disk that we know and we have images for, we're emphasizing the diversity of all these protoplanetary disks. And hopefully we're starting to be in a point where we have enough of them to be able to tell some statistical trend out of them, instead of just looking at saying just like, oh, look, there's a beautiful image right there. And I think I'll stop here and take questions. Thank you.
Yeah, nice job mimicking Cal, by the way. So now you have a dozen of targets. I just wonder, do you see, and some of them seems to have different H/R ratio. Do you see any correlation between the scale height over radius with any other properties of the systems?
So we haven't quite done enough modeling on all the sources to give you a final answer on that. What I can say is that in all but 2 of the edge-on disks for which we have done modeling, the scale height we're finding are just consistent with basic vertical hydrostatic equilibrium support with nominal temperatures in the midplane. So nothing fancy about it. The distribution of flaring with distance is typical, normal, an exponent of 1.1, 1.2, something nothing out of the ordinary. We haven't looked at trends versus other properties yet. Again, it boils down to doing all the modeling for each of the individual sources. But as far as I can tell, except for a couple of objects that look too thin vertically, and that's probably due to some form of settling or something like that, apart from those 2 objects, most of them look just like you would have expected from textbooks.
I see, because I guess one of the interesting issues would be try to see whether the disk becomes thinner as they get older, I guess, because you have a large enough sample, so presumably you would be able to actually see this issue here.
I'm not sure we will be, and I think the reason for that is selection bias. So we've picked up our edge-on disk from their SED, right, to have the double peak structure. And to have the double peak structure and see scattered light all the way to 10 micron, you need the disk to be extremely optically opaque to have that happening. And once you do that, you're in the regime of the most massive disks, and you're getting whatever they are, but that's the most massive disk, at least dust-wise, that we can find. And that's a severe selection criterion that may not be telling you so much about the disk evolution overall without proper disentangling of other properties, let's say. So I'm really worried about selection biases there.
I see. Thanks.
In the 2 examples you give in binaries with misaligned jets, do they have common proper motion?
I believe that
they're not projected binaries, right? You can establish they're physically related.
So I believe there's no, let's put it that way. There is no proper motion evidence that they're not related to one another. The problem is that they're in star-forming regions, right? So we're talking 150 parsecs away, and the proper motion is relatively low. So the one thing we can establish for sure is that they're both members of that star-forming region. But if one of them was, a few parsecs away, how could we tell? They would still presumably be moving in pretty much the same direction. So you cannot have firm evidence for like 300 AU binaries that they're actually really physically bound, as opposed to just 2 stars in that star-forming region. Then there's a statistical argument. What's the likelihood of getting two T-Tauri stars in projection within 300 AU in something like Chameleon, which is not super rich? It's pretty low. Doesn't say that it wouldn't be the case. It could still be true that they're not related. But it's a statistical answer.
Okay, we have time for one more question.
Hi, I'm very interested in the angle you have between the jet and the disk. Is that the first time there is a slight misalignment between the disk and such a jet? Or?
That's the first one I'm aware of, where the angles can be measured with great accuracy. I mean, in some cases, you look at earlier, more embedded objects, you have giant outflows, they're pretty broad. So there you could, even if you see a few degrees offset, you might say, well, it depends on how you measure your angle exactly. In this case, the H alpha jet is very narrow, very well collimated, it's very well defined. The disk midplane is also very well defined. Now, the one thing we don't know is whether there is anything like some form of a warp or something like that, and that the inner disk may be misaligned with the outer disk. What we're seeing is the midplane in the outer disk. So that could be, that we cannot see because we cannot see through the disk at this point. So we don't have the answer for that.
Okay, great. Let's thank Gaspard again.